Hey, how's everybody doing today? We're just plowing our way through Chapter 9, Radicals. So we're going to continue on with some more product rules, quotient rules, rules for radicals, what we can do, what we can't do, simplifying, that kind of stuff. You can see from the homework up on top, it says Part 1. I have split 9.3 into two different sections. There's a nice break. This first part is all about radicals, and then the second part is all about using those radicals in a more of an application sense. So it's a nice split for this. You can do them all at once if you want, but I'm going to have two different lectures for those. Okay. All right. So let's first of all take a look at what the product rule says. All right. We have for radicals we have a product rule and we have a quotient rule. The product rule says that if I have two things multiplied, not added, but multiplied, each piece can get its own radical sign. All right, now I can go this way and split it, or I can take these two and combine them. All right, now the only way that I can combine them over here is if this index and that index match. Okay, if they're different, then I can't stick them underneath one. Then we'll look at different ways of reducing those. And then we also have the quotient rule. I might as well just throw that out here right away. And it's the same concept, just with division. That if you have something divided underneath a radical, you can split it. Or if you have two pieces with the same index, you can combine them under one. All right. Now, what are my rules on simplified radicals? Well, there are a few rules. Okay, so a simplified radical cannot have a perfect nth power in it. What does that mean? Well, we'll talk about that later. All right. It can't have more than one radical sign. Unless we're adding and subtracting, that's just going to be an exception to the rule. But all these were all multiplying and dividing, so that's different. Okay, so we can't see how this one has two. So it couldn't possibly be, unless it's not simplifiable. Is that a word? Simplifiable. No. Unless you can't simplify it. Okay, so you can't have more than one radical in it. Can't have a radical in the denominator. It's a big no-no. And the outside pieces, okay, meaning the parts that come out of the radical need to be in simplified form. And I think it's just going to be easier just to go through these when we hit them than me trying to make stuff up. Okay? So, product rule. It says multiply using the product rule. Well, yeah, that's going from this to this, right? So if I have the square root of 3 times the square root of 7, that's the same as the square root of 3 times 7 because my indexes are both 2's, which is the same as the square root of 21. Is that true? Well, let's check it with the calculator. Is the square root of 3 times the square root of 7, which is that ugly decimal, the same as the square root of 21? Yep, exactly the same. So now what I'm going to do is I'm going to go back into my simplified radicals. All right, these three things have been satisfied. I only have one radical sign now. It's not in the denominator. And my outside pieces don't exist. I don't have anything on the outside of the radical here, so those can't be simplified. But this one's a very important one. Since I'm in square roots, I have to look to see if I have a perfect square in it. Well, what's a perfect square? Well, let's make a list. My suggestion to you is to make a chart. I'm going to make it over here. Okay, so we're going to have squares, cubes, and fourths. We don't need fifths and all that in this particular homework. At least I didn't in the beginning. Yikes. It's hard to do. You guys don't realize how awkward this pen is. So now I'm going to take my numbers down here. 5, 6, 7, 8, and dot, 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 dot. Okay, so I'm not going to do all of these, obviously. We could go on forever. But what I want you to do is I want to say, okay, I want to do all my perfect squares. These are my squares. 1 times 1, 2 times 2, 3 times 3. I'm multiplying each one of these numbers twice. So I have 1, 4, 9, 16, 25, 36, 49, 64, and so on. Dot, dot, dot. Now I'm going to do my perfect cubes. Okay, 1 times 1 times 1, 2 times 2 times 2, 3 times 3 times 3. That's what I'm doing here. So I've got 1, I've already calculated these out, so 27, 64, 125, 6 is 216, 7 is 343, and 8 is 512. Okay, I'm multiplying each one of these by itself 3 times. And then I'll do it for the fourths. I think that's as far as we need here. So I'm going to multiply 2 times itself 4 times, 3 times itself 4 times. Okay, and I'm getting large very quickly. So we don't have to go up very high. 256, 625, and 1296. Once we hit, I mean, my gosh, once we hit the thousands, good to go. So when I look at my 21, I'm going to look to see if there's any of these inside of it. Meaning, can I split that into 2 numbers multiplied? Well, no, the only 2 numbers that multiply are the 3 and the 7. I mean, like if I had a square root of 20, I could certainly work with that. Isn't there a 4 hiding in there? Isn't that 4 times 5? So that's what we're looking for. So since there's only a 3 and a 7 in here, I don't have this yet, I don't have a perfect second power in it, so I'm done. So the product rule says square root of 3 times square root of 7 is the square root of 21. So we're finished there. Okay? Well, they're not going to always be that nice and neat and simple. All right, I have 2 cube roots. My index is the same, so I can combine those. Right? Where am I? I'm right here. I've got the cube root of 10a times the cube root of 2b. Well, I've got multiplication. I've got 10a times 2b. And I can always multiply my numbers, so I've got 20ab. So I've got the cube root of 20ab. All right? I don't have any perfect third powers in there. I can't split a 20 into any of these numbers. So I should be done then. Isn't it right there? Cube root of 20ab. Excellent. All right, so now I'm going to use my quotient rule, right? What was my quotient rule? This. All right, I'm going from this to this. So I've got the square root of 4/25. I can split and evaluate each one separately. The square root of 4 is 2, and the square root of 25 is 5. So my answer is 2/5. Should we check that? I've got 4 divided by 25. And I'm saying that's the same as 2/5. No, I'm not. I'm saying that's the same as 2/5. Not the square root of 2/5, just 2/5. So yeah, they're the same. Okay? All right, so k over 64, should we do the same thing? Absolutely. Okay, I can split. Now what do I do with this? I don't do anything with it. I can't. Square root of k is just a square root of k. It has to stay underneath the radical, just like this 20 and the a and the b had to stay underneath there. Okay? All right, I'm not going to do all of these for you, but I'll do a few of these. So now we're into the fourth root. Did I go up high enough? I did not. Oh my goodness. 6,561. That's ridiculous. So let's see if that's a perfect fourth in itself. I'm guessing that it is. So we're going to hit a number 4. Math, we want the x through it for 5. Let's see if that's a nice perfect fourth. It is. The fourth root of 6561 is 9, so that's going to help us out a ton. Okay. So we're going to disregard that negative sign first of all. X to the 8. Okay, so I'm just going to keep carrying it with me. I'm going to split this apart, 6561 over the fourth root of x to the 8th. Just keep carrying that with it. So that would be a negative 9, right? Because this piece of it up here is 9. What about this denominator? Well, you can look at it as groups of 4. How many groups of 4s can I get out of 8? Well, I can get 2 out of there, right? Another way to do that is to turn it into an exponential and evaluate it that way. Okay, so I've got 2 groups of 4s out of 8. So there's my answer. This has to stay underneath. It wasn't a denominator and it can't pop up to the numerator ever. Okay? All right, square root of 63. So what we're going to do is we're going to first of all check to see if that's just like that 6561. Is that a perfect? No, it's not. It's not a perfect square by any means. Okay? We know that because the square root of 64 is. All right? But we're just going to check to make sure that that's not perfect. Well, now I have to go back and say, look at my rules. Well, I only have one radical. It's not in the denominator. I don't have any outside pieces. But do I have a perfect nth power in it? A perfect square within a 63? Can I break my 63 into any of these numbers? Well, sure. Isn't 63 9 times 7? That's what I want to do. So my square root of 63 can be rewritten as 9 times 7. Now using my product rule, I can split these. Right? This piece is 3. This piece is square root of 7. I can't do anything with that. So before you would, let's say you're in a test situation, before you proceed, make sure you check it. Is the square root of 63 the same as 3 times radical 7? Yep, exactly the same. Now, this is satisfying all 4 of those conditions because there is no perfect square within a 7. So I'm finished there. So 3 roots of 7. So don't put any spaces in between there. Just type it in. I'm not going to check all of these. Same thing here. What's hiding inside a 12? Well, there's a 4 in there, isn't there? So 12 can be broken apart into 4 times 3. I'm trying to pick out the biggest perfect square that I have within there. And then I can split, and then I can evaluate. This is 2. So this is finished. Okay? All right, we're going to do the same thing with our cubes. We're going to go back to my list. Now, I don't know what's inside of 162. So I'm going to start here. I always want to work backwards. I don't want to work frontwards because I want to find the biggest perfect cube, not the smallest. Now, obviously 125 can't be divided in there because that's so close to 162. So I'm going to start with the 64 and just see if it's in there. So I'm going to take the 162 and divide it by 64. Nope. Then I'm going to take the 162 and divide it by 27. That's my next shot. Oh, there it is. So 162 is 27 times 6. That's why this chart is super helpful. So now I have the cube root of 162 is the same thing as the cube root of 27 times 6. Now I can split each into their own cube roots and evaluate. The cube root of 27, I go back to your chart, cube root of 27 is 3. Okay, or you can use your calculator if you've forgotten. So this is the same as 3 times the cube root of 6. Well, we can check that with the calculator. We can see option number 4 is a cube root of 162. We can see what kind of a decimal we get on that. And now we want to do 3 times the cube root of 6 and see if that's the same. It better be, otherwise we've done something incorrectly. But it's exactly the same decimal, so we're good to go. There is no perfect cube still sitting within a 6, so we're finished. Okay, I'm going to let you alone on some of these because these just go on and on and on. All right, let's take a look at this one. This one's a little different just because we have those variables. 169x cubed y 11. Okay, so I'm going to do the same thing. I'm going to break these things apart. Well, first of all, I'm going to check to see if 169 is a perfect square, and I know it is. It's 13 times 13, but if you didn't know that, we're going to test it out. Okay, so that's good news. All right, so I'm going to break this into, this one I don't want to break apart because that's a perfect square within itself. But look at this. If I was to take the square root of x cubed, that is x to the 3/2 power, which is fractional, which is not going to help me. This is not the way we want to go. So what I want to do is, I know I need groups of 2's. How many groups of 2 can I get out of 3 things? Well, I can only get out 1, so I want to do 1 group of 2, and then I've got my x left over, right? This is all multiplication in between. Because isn't x squared times x to the first, using my exponential rules, by adding x cubed? It sure is. Okay, so I want to split this one. Same thing here, I've got 11. How many groups of 2 can I get out of there? I can get 5 of them, can't I? How many are left over? 1. No, that's 5 on the outside, Simone. I was going to go, what is wrong? Let me just get my eraser out. Sorry about that. Okay. I love that eraser. I think it's so cool. All right, I'm looking for groups of 2, right? So I can split it into, what I'm really doing is I'm looking at this number and saying, what's the highest power that I can break it into that's divisible by 2? Well, 10 is the closest. It comes out as a 5 on the outside, so I just jumped the gun there. So I'm going to split this into something that is divisible by 2 and whatever's left over. I've got 1 left over. Now I'm going to split this into 2 different pieces. I'm going to put all my perfect squares here and all my non-perfect squares there. So this one was perfect, and that one was perfect, and that one was perfect. So I'm going to group those over here. Okay, and I'm going to take out the pieces that aren't and put them over there. Now I can evaluate. Each one of these can come out. Okay, now I'm only going to do this once because there's got to be some steps that we can skip. But each one of those can get its own radical sign. The square root of 169 is 13. The square root of x squared is x. And the square root of y to the 10th is y to the 5th. Now why is that? Because remember, square root of y to the 10th is the same as 10 over 2, which is 5. So you're always taking this divided by that, this divided by that, okay? And then we have the xy left over. So it's 13xy to the 5th times the square root of xy. Should we check that out? Let me just drag that up a little bit so I can see it. Let's test that out. So we've got 13xy. We're going to raise the y to the 5th power. We want to drop back down. We want the square root of xy. Excellent. Okay, that's as factored, excuse me, factored and as simplified as possible. All right. Same thing here. Well, this one's not actually the same thing. These are both perfect cubes, aren't they? 8's on my list. 8's a perfect cube. It's 2 times 2 times 2. And anything that's divisible by 3 is perfect, right? 12 is definitely divisible by 3. So just because I can, I'm just going to write this one out. I need a new screen here. So 8 t to the 12th. I can just, this is like a -1, okay? And then we've got, that's the negative there. And then we've got the cube root of 8, cube root of t to the 12th. Okay, this is still a -1. This comes out as a 2. This comes out as a 4. T to the 4th. Remember, t 12 over 3 is t4. Okay, so this would be -2 t to the 4th. Okay, I can always multiply those back out. All right, that one I'm going to leave you alone on because that's exactly the same thing. Those are all perfect cubes, I do believe. So we are going to see what you can do with that one. Isn't 343 a perfect cube? Now remember, you can always just quickly check it here if you don't know. If you don't have that list in front of you, you can always use a calculator for that. So yeah, 7 times 7 times 7. Don't forget that this is a -343, which is a -7, right? -7 times -7 times -7 will give us a -343. But then that becomes a positive because of this one. So 1 in, 1 out. We've seen that before. That one's the same as the others. That one's pretty much the same. Well, we can just do one of these, I suppose. We have -1 times the square root of 8b to the 9th. Okay? Just keep dragging that. I'm going to split. The biggest perfect square within an 8 is 4. Right? 4 times 2 is 8. And if this is 9 and I want groups of 2's, I'm going to have my next closest is 8. And I've got 1 left over. And again, I'm going to split this into its perfect components, its not perfect components. This and this are perfect, so we've got 4b to the 8th. What's left over is the 2b, or not to be. Now these can come out, so we've got a -1. They can come out individually. Square root of 4 is 2. Square root of b to the 8th, you just take that in half. 8 halves is 4. And then you can just combine those. So there's nothing new there. Okay? You're going to get lots of practice. Same thing here. We're grouping in groups of 3's. I should have done this one instead. Now I got to do both of them. X13, Y14. Okay, so is 270 a perfect cubed? I doubt it. 270, I really don't think it is. Nope. But there's got to be one within it, you would think. Go back to your list of perfect cubes. All right, we're at 270, so we want to start at maybe 125, which I don't think is in there either. But we can start there. I've erased the list, but hopefully you've got it. That one doesn't work. The next lowest one is 64. Sometimes nothing goes into them, and then you just leave it alone. 64. No, that one didn't work. What about 27? Ah, I can see it's already there. It's 27 and 10, isn't it? I don't even need the calculator for that one. All right. So when I split this number, okay, I'm going to split my -27, and then I've got my 10 left over. I'm going to choose to take my -27 in because I can grab that out because this is odd. I'm not going to leave it in here. Right now I need groups of what? 3's. So how many groups of 3's can I get out of 13? Well, the closest is 12, right? 12 is divisible by 3, so that would be 4 groups. So I want to make this into a 12. I've got 1 left over. That still is 13. I'm just rewriting these. I'm not changing the values. And same thing with my y's. I can get 12 that'll be 4 groups, and then I've got how many left over? I've got 2 left over this time, right? Because this is 14, this is 13, this is negative 270. So now I split. I split them, man. I put my perfect cubes, that one, and that one over here. So I've got a negative 27, x12, y12. And my loser pieces, which are not perfect, 10x y squareds. Okay, so now all of these come out individually. The cube root of a negative 27 is a negative 3. Negative 3 times negative 3 times negative 3. This is 12 thirds, which is 4. Remember we said we grabbed 4 groups and 4 groups. And then we have the leftover 10x y squareds. Okay? I'm pretty sure you know how to enter all that in. You've got powers and you've got a radical. Cubed. So you're going to want, definitely this one. Okay? I'm not going to take the time to put that in there though. And here, same thing, you're just doing groups of 4s. Here, this one's perfect. This one you're going to have to bust into a b to the 20th times b to the first, right? Because 20 would be the closest number that's divisible by 4 with 1 left over. I think 243 is on my list. Nope, it's not. You can see if something goes into it though. So I'm going to leave you alone on that one. Well, let's do that one, huh? That one looks a little different. Not much. So I've got v to the 15th over 100. So my instinct is just to split right away. That's what I would do. All right, so now I need groups of 2s, right? There's a 2 here. So what I can get, the closest would be 14, and then I'd have 1 v left over. So that's still v to the 15th. And the square root of 100 is 10, so that one's nice and neat and easy. Now I'm going to split this into it's perfect and it's not perfect. And this comes out as how many? 7. 14 divided by 2. We got 7 groups. This one stays in and that one is out. Now here I have some outside pieces, don't I? I have a v to the 7th divided by 10, but these are not reducible. Let's just say I had a 5v to the 7th. See, now I've got 5/10. That's definitely reducible. That's what it means by the outside pieces need to be reduced, but I don't have that there. All right, what else do we have? Well, I can't make 28 to the 5th power. I can't make 10 groups of 10 out of 5. That doesn't even make any sense. But I could use my exponential conversion. So isn't this the same as 28 to the 5/10 power? Which is equal to the 28 to the 1/2 power. So really what I'm working with here is the square root of 28. Now square root of 28 isn't finished because it has a perfect square underneath there, doesn't it? Isn't there a 4 in there? 4 times 7. Split. Two roots of 7. Let's try it. That's why I want to just make sure. 2 roots of 7. Nice work. Let's check it with a calculator. Let's say this was a test. I want the 10th root of parentheses 28 raised, no, well, I can do that, right? 28 to the 5th power. Or I'm saying I can also do 2 times square root of 7. Those should be exactly the same decimal, and they are. So in a test situation, just use all your resources and use them wisely. Okay? Same thing, right? 36/16 can be reduced. Okay? Oh, what is going on with this one? This one looks different. Square root of 5 times the cube root of 3. Okay, wow. Well, I can't combine these with my product rule because I don't have the same index, right? So we're going to force them to be the same index, and then I can get them together. Okay, so I'm going to write each one of these as exponents. I'm going to put the pieces that I need in there. So this is the same as 5 to the 1/2 power times 3 to the 1/3 power. I'm going to change these. I don't want 1/2 and 1/6 or 1/3 because I've got my indexes are different. So I'm going to find my LCD of a 6 and I'm going to turn both of these into sixths. Okay, so I'm going to build it up. 2 goes into 6 3 times. 3 times 1 is 3. This is where the calculator is not going to help you. 3 goes into 6 2 times. 2 times 1 is 2. So this is the same as 5 to the 3/6 power times 3 to the 2/6 power. I can't add these because my bases are not alike. Okay, but I'm just changing them so my indexes are. So I'm going to go back to more of a radical form. I've got the 6th root of 5 cubed times the 6th root of 3 squared. Now I have the same index, so these can be combined into one radical. And I have 5 cubed times 3 squared. I'm thinking it's going to want the 5 cubed times 3 squared. I don't know. 1125. Now I'd also have to check to see if I've got a perfect sixth within that. I don't know. I have no idea if I do. I'm guessing I don't. Let's just see. I don't think it's going to go into, I don't think it's going to go into 6th powers where you have to start pulling stuff out of huge numbers like this. But on a test situation, you know, I would make a list of your perfect sixths. I would check it. You know, this is homework. So homework's different. But on a test situation, well, okay, 6th powers, I better check it out. I better make sure that I don't have a perfect sixth within there. This one's done the same way, so I'm not going to do that one. So that's 9.3 part 1. We'll get to 9.3 part 2. It's a nice break. We're going to look at the Pythagorean theorem and the distance formula and some application problems, and then we'll switch to 9.4. So I'll see you then.